Okay, off we go. So here's where we were last time, which is a while ago. Of course, we had an exam yesterday, weekend before that. So it's been a while. So here's the last example that we did, just to kind of remind you of kind of what we were doing. The big question of this example was to compute how much work it takes to move along a certain path, exerting a certain force, in recognition of the fact that, of course, we're pushing against the force that was listed. Real quick digression: you always have to look at the phrasing of the problem to see which force you've been given. This is unfortunate, but it's the nature of the world. Sometimes you'll be given the force that you are exerting and is the correct force to use in the formula. Sometimes you will be given, it's just the way the world is, the force opposite that you are opposing, and then you have to remember to insert the minus sign. So heads up, and always interpret it. Don't try to create a rule of thumb on this. Make sure to understand the context and interpret accordingly. Okay, so you want to compute work. Well, this was our motivating example that led to vector line integrals. So we've already developed that this vector line integral is how we would compute that work. And then it's just very plug and chug, right? We have these formulas up here. If you want to compute a vector line integral, there you go. That's the pullback integral straight from the parameterization, everything in terms of the parameterization. And we did this computation last time. Here was our parameterization. We took the derivative. That gets inserted. Everything's rewritten in terms of t. Done. Okay. And then where we ended last time was making the observation that, you do have to worry about the parameterization and whether that matters. And in most ways, the parameterization doesn't matter. But there is one very important detail, and that is we are not parameterizing a curve. We're parameterizing an oriented curve. The orientation matters. The orientation is part of the important description of what it is that we're actually doing, right? So when you parameterize, you have to parameterize the correct direction if you want to get the correct answer. And if you don't parameterize, right, if you're going the wrong way, then you're going to be off by a factor of -1 in every single term in your integral, which means your answer will be off by -1. Which, as I recall, the way we ended last time was in recognition that even though, if you're going the wrong way, then you'll get the wrong answer by virtue of a minus sign. Notice what that means then is that the thing that you actually wanted, right there, easy to solve for. It's the negative of the integral you computed when you did it backwards. Right? So that's something to keep in mind. So let's see how that plays into the next example, picking up now with new material. There's actually, I'm going to discuss 4 different ways of solving this problem, 3 of which I like, 1 of which is a little awkward, and I'll get to that in a minute. The question is, same as the previous, but what if we're walking clockwise instead of counterclockwise? So let me show you the 2 direct ways to do this first. And by direct, what I mean is we are going to parameterize this curve clockwise, like so, in other words. Right? We start here, we end there. How do we parameterize clockwise around the top half of the unit circle? So we can't just say cosine t, sine t, that's counterclockwise. All right, so there's a couple different tricks for doing this. I like both of these. And again, as y'all will recall, I'm not a here's how you do them kind of guy. I'm a here's some tools for your toolbox kind of guy. I think that's the right way to be when you're learning material of this sort, because there's so many different scenarios. Different tools are useful in different circumstances. Right? So here's the first tool. The first tool I want to just note is try to identify in your picture where is your parameter. Try to point to it to the extent that you can. right there in your picture. So if I'm going clockwise, in other words, if I'm doing this, right, then notice this angle right here is a pretty natural candidate to be the what I'm going to call T. You know, I like to call my parameters T. Most people do. This angle right here is a natural parameter because notice at the start of our clockwise path around this curve, at that start, this angle is 0. So we start at t equals 0, and then notice as I move, as I go sort of along this curve in the direction in question, note that this t is increasing, as a parameter should as you move along your curve. And then notice that it ends at t equals pi. So I think that's a pretty reasonable candidate to be our selection of our parameter. That's our t. Now, how do I use that to parameterize the curve? In order to parameterize the curve, of course, I need position as a function of t. So I need to look at this picture here and figure out how am I going to identify x and y in terms of t. We don't have trig set up around this picture. Right? It's that's the wrong angle. What we have trig set up around is this angle here. Right? That's the classical, if you have an angle and you want to talk about the location, well, cosine and sine are based off of that angle. So that's the big idea. Our location is just cosine and sine, but very importantly, cosine and sine of this angle, not t. Everybody on board with that? So, of course, what we want is to have this written in terms of t, and so to write this in terms of t, of course, just a little bit of algebra, no big deal. I've noted previously that I think all students in this course, and really all students in any math course above a certain level, really ought to know the angle addition formulas for sine and cosine. They're not hard. Look them up. Make sure you have them memorized. Right? It's I think prerequisite to the course, and easy plug in, and you get this as your answer. Okay, how we doing on that? Everybody's happy. Let's look at the next tool for your toolbox, and that is this is a different way of coming at it. I want to parameterize this curve clockwise. All right, I want to get a formula for position on that curve as a function of t. I don't have it yet, but what I do have, I have a pre-existing formula for this curve, the counterclockwise oriented, same underlying curve, right? But oriented counterclockwise. That's our old friend, cosine t, sine t. Nothing to it, right? So what I have and what I want, you notice pretty quickly. And again, thank you, picture. The picture is what tells the story here. Notice these are literally reflections of each other. These are reflections over the y-axis. And when you do a reflection over the y-axis, the formula for that reflection, right? This is how you reflect over the y-axis. Notice that leaves the y-coordinate the same. Notice that changes the x-coordinate by a minus sign. And so with that in mind, we do that reflection just with that minus sign right there. Is that cool? All right. And so now with this formula, right, and notice in both cases we've got the same formula for the clockwise oriented parameterization. Position is the same formula, whichever way you thought of it, whichever tool you use to derive this, right? And what do? Well, you've got to go through and do the integral and plug and chug to compute, and there's your answer. Everybody happy with these first two? Okay. All right, here's the third method. The third method's way better. The third method says, oh, yeah, we want to go clockwise. Okay, well, clockwise is just the opposite orientation from counterclockwise. That's easy. Right? What happens when you take an opposite orientation? Well, an opposite orientation just means you're going to get a minus sign. Oh, and wait a second. How do I compute the integral over the original counterclockwise oriented curve? Oh, we already did that, right? Going counterclockwise, we already did all the plug and chug previously, right? We got, for counterclockwise, our answer was pi. And so, just like with these other, wrong button. Just like with these other computations that gave us the clockwise work to be minus pi, this argument also gives us the same answer, minus pi. Notice I'm not reproducing what's basically, very, very similar plug and chug, right? Slight little details of minus signs. I don't have to go through that whole detailed calculation again. I can just reference what I have in green there, the old calculation, account for it appropriately, and done. Everybody with me? Okay. All right. Okay, here's the fourth way to do it. I don't care for this fourth way to do it. There's some real sketchy ideas. Let me say it differently. What I'm about to show you can be argued perfectly reasonably, perfectly rigorously as a valid computation. But I don't want to go through those details. There are some real confusing little bits. There's some dangerous little landmines. There's some easy mistakes to make along the reasoning that it would take to justify the method I'm about to show you. And the payoff for the method I'm about to show you is zero. Basically zero. So it's not worth it, is my gripe. So here it is. A lot of students like to say, okay, well, we already have... again with the wrong color. Let me put this into... Yeah, okay, so we already have the counterclockwise parameterization. Right? And so if we want to go clockwise instead of counterclockwise, we'll take all the same stuff that we did for the counterclockwise, and we'll make it clockwise by, instead of going from A to B, we'll go from B to A. Right? I mean, you can see the attraction there, right? Seems like that ought to be a reasonable way to do it. So this really does give rise to some problems. In the integral, when you write down the integral, the Riemann sum that this represents, it's all perfectly well defined, no problem, and your dx vectors go the other way. But you're still using the counterclockwise parameterization, which means that your velocity vectors still go in the wrong way. So in this scenario, the dx is not x prime dt anymore. This is uncomfortable, right? And again, it's not about the answer; it's about the ideas. So the argument I'm going to make here is that in order to justify this approach, in order to make this make sense, there's a bunch of delicate, careful setup and reasoning that has to be done that we're not going to do. So I'm gonna put a frowny face next to this. It's not that it's wrong. It's that I don't believe a student who writes this has thought through those necessary thorny, little delicate but important details. And again, keep in mind it's about the reasoning, not the answer. So the fact that this will give you the right answer is irrelevant, right? So this is not believable reasoning. I'm going to say it that way. Okay, so please don't do this. Again, I will not believe that you understand all the necessary reasoning behind it. And what do you get out of the deal? What do you gain by being able to do this? Notice all that does is insert the minus sign that is perfectly validly noted there per this theorem here. So when you have this on the table, right, there's really nothing to be gained by this sketchy. Notice that this means time is moving backwards. It's very sci-fi. It's very, it's very. I don't know. I'm uncomfortable. Right. So please don't. I don't buy it. Okay. All right. Let me get rid of this mess. Okay. Moving along. So here's a new point of view we need to investigate. We have seen that when our vector field represents forces, then the vector line integral computes work. This is our motivating example. This is why we wrote down and decided that we liked vector line integrals in the first place. You give me a force, this computes the work. Okay, here's the thing though. Keep in mind, sometimes vector fields represent fluid flows. Okay, well, if a vector field represents a fluid flow, then it's not a force. That means the vector line integral, it's not going to be work. It's not going to represent work anymore because that assumed the vector field was representing forces. Well, what does a vector line integral represent if the vector field is representing a fluid flow? What's the physical interpretation? Rhetorical question. What is the physical representation of a vector line integral in this new scenario? So here's the bad news. It's not a physical notion that you've seen before, probably. It'd be nice if it was some simple thing where I could say, this thing that you heard of back in your high school physics class, yep, that's what it is. It's not. Right? So there's a temptation to say, oh, well, then it's not a thing and it's just a bunch of garbage. But that's not true either. There is a new physical idea that vector line integrals represent in the fluid context. And so that's what I want to talk about now. What I have here is just here for student convenience. Basically, this is nothing new. Everything we have there is just our established players, the participants in discussions about vector line integrals. So that's just for easy reference. So how are we going to answer this question? I'm basically going to start with the answer. I'm going to ask a question seemingly out of nowhere. And the answer to this question is going to, roughly speaking, it's going to heavily, basically involve a vector line integral. So it's going to look like this is the question and vector line integral is the answer, but it's more honestly the other way around. This is basically going to end up being the answer to the question of how would I interpret a vector line integral. Right? So anyway, but let's not get the cart before the horse. Here's the scenario that we have. We have some curve, and I want to entertain the idea of there being a fluid in here, kind of in this vicinity of our curve, specifically as defined by looking at this cross-sectional area. So around our curve, I want to imagine that we basically kind of drag these little areas along the curve, and that will make this thin little, it's tempting to call it a tube, but let's not think of it as a tube because it's not confined. This is just a bunch of fluid. It doesn't have to, the fluid's going to be flowing every which way. It's not stuck in the tube. So let's not think of it as a tube. Okay, so that fluid having been defined, here's again the big question that we're going to ask. That's eventually going to be an answer, but we're going to phrase it as a question. Okay, well, I've got a bunch of fluid. The fluid is flowing. To some extent, that flow will be along the curve. To some extent, it'll be perpendicular to the curve. If I for whatever reason that will become clear later, if I decide I'm only interested in the extent to which the fluid is flowing along the curve, how would I compute that sort of total, all of the fluid, looking at how much it flows along the curve? How do I add that up? And this is a very straightforward calculation. Now again, I remind you, not at all clear why I'd care about this thing, but we're computing it anyway. And here's how the calculation goes down. Again, I've got this curve here. I've got little pieces of fluid here that I'm going to call dV that are pretty easy to see, or just area times length. Right, there's a little piece of fluid. I can pretty easily write down the extent to which that fluid is flowing along the curve. The extent to which the fluid is flowing along the curve is going to come from looking at the velocity. And keep in mind, our vector field represents the velocity of the fluid. So that's the direction the fluid's actually going. But again, we are interested only in the along the curve portion, which is this component, which is computed like so. Is that cool? Alrighty. All right, so we're kind of done. I mean, not quite, but it's all over by the shouting, because we want to look along, the total along the whole curve. So we're just going to add up these little pieces, this quantity that I'm interested in, right? This dq, little pieces of the fluid, and how, to what extent those flow along the curve. We just got through computing that. So I just plug that in. Area is a constant, so it factors outside of the integral. And there's our answer. So again, reminder, we've asked a question that we're not sure why we're interested in. Right? And we have an answer. So now here's where we're starting to make sense out of that. This question that we have asked, this quantity that we just computed, notice that it's area times vector line integral. So I'm going to take this computation, this result that we just got, and I'm going to sort of move things around and interpret from this conclusion how to think about vector line integral. I mean, other than this factor of area, the line integral is the quantity that I've just computed, except for that factor of area. So all I have to do to account for that is sort of recognize that this area, I could, kind of, if you will, I could kind of divide it over here to make it, put it in the denominator, right? And then I'm just going to, with that in mind, say, that's a little messy actually. I'm going to say per cross-sectional area. Vector line integrals, what they represent in the fluid context is, with the understanding that, of course, it depends on what your cross-sectional area is. Vector line integrals represent the total rate that the fluid is flowing along the curve per unit area. That makes sense? So this is an interpretation. Again, it's not a familiar concept. It's not like, this is, that old idea from high school. No, of course not. Brand new idea. You've probably never seen it before. But that is I think, the most natural interpretation of a vector line integral in this context. So let's see some examples. Real quick, I am going to give you a quick definition. We'll motivate this definition momentarily. A vector line integral, in the scenario where the curve is a closed curve, very importantly, this little discussion we're about to have down here is only for closed curves. The curve starts and ends at the same point as I've drawn here. Here's some closed curves. Right? Notice they start. Whoops, I'm going the wrong way on that one. Starting and ending at the same point. Yeah, that's closed. In this scenario where you're talking about a vector line integral around a closed curve, then we refer to the vector line integral as being a circulation. So let me show you some examples of how we would think through a circulation from a picture. So here, for example, let's imagine this closed curve right there, right? And I've got this fluid flowing as per the vector field I've indicated here. And I'm interested in, it says right here, the vector line integral. How would I infer the vector line integral from this picture? And keep in mind, our interpretation up here is that vector line integrals per unit area, of course, are basically telling me the extent to which the fluid's flowing along the curve. So let's look down here in this picture. To what extent is, in this case, the fluid flowing along the curve? And actually quite a bit. Right? So, for example, along in the vicinity of that point, the curve is going that way. The fluid also going that way. The fluid is flowing, as I have it drawn, seemingly almost exactly along the curve. Does that make sense? And so, hopefully, no surprise that we get a positive circulation there. Is that cool? Now let's talk about the terminology. Why would we call this circulation? What's the motivation for the term circulation? Well, notice we're talking about the extent that the fluid is flowing along the curve. The fluid is flowing along the curve. But wait a minute, the curve being closed, the curve kind of goes around in a circle. So if the curve goes around in kind of a circle, if you will, and if the fluid is to some extent doing the same thing, then what we're detecting is the extent to which the fluid is kind of rotating. To what extent does the fluid represent like a swirl of some sort, like a little, I guess you'd call it an eddy current or a little whirlpool kind of thing in your fluid flow? Does that make sense? Okay. All right. Which I think makes this terminology circulation pretty natural. Okay, now we do have to worry about minus signs. So, for example, let's think about this curve right here. Note it's oriented the other way. It looks an awful lot like the first curve, but it's importantly different. Again, orientations matter. We're interested in oriented curves, not curves. That curve, with the fluid still going the same way, to what extent here is the fluid flowing along the curve? Well, it's going the wrong way. It's going backwards. Almost exactly backwards, right? But backwards, and so in a case like this, you should expect circulation to be negative. Said differently, same idea said differently, when the circulation is negative, that suggests that the direction that the fluid is rotating is opposite of the direction that the curve is oriented. And think of the orientation of the curve as sort of the parameter of the question. You know, the question being asked here is, to what extent is this fluid flowing clockwise? Answer, it's quite the negative. It's counterclockwise. Is everybody buying it? All right. And by the way, these two scenarios were both, set up for maximum convenience, for maximum simplicity. There are some sad scenarios like this. In fact, most scenarios are kind of like this. That is really kind of hard to tell. Along in here, the curve is going that way. The fluid is going kind of not that different. So that looks like positive circulation. On the other hand, along in this part of the curve is going that way, but the fluid is going pretty much the opposite way. So I see some positive terms here. I see some negative terms. And then the big question is, who wins that tug of war between the positive terms and the negative terms? And there's a little hard question, and not immediately clear from just looking at the picture. Okay. Okay. Last little bit I want to note. I think this is a nice point of view. In some sense, what we're measuring with circulation is the extent to which the fluid is kind of rotating. But of course, the fluid's doing different things in different places, and so it's kind of hard to get our hands on that. But the idea is if you have some small object, and for me, I like to imagine a leaf that has fallen off of a tree into a little river or creek or something like that. So here's my fall colors, dead leaf that has just fallen into the water. And what's going to happen? What's this water flowing as I have indicated? What's that going to make that little leaf do? Well, it's going to make that leaf kind of twist, kind of turn, rotate. Does that make sense? Yeah. So that's one way to think about circulation. Circulation is a way of getting our hands on the idea of how would some small object floating in this liquid, in this fluid, how would it be turning? How would it be rotating? And I appeal to your physical experiences. If you've ever noticed, some leaf kind of in a river or creek or whatever, just kind of floating downstream. They might go in a straight line, right? But sometimes they're turning as they go. And that's because the fluid flow has some sort of a circulation that's going on that's making it turn. Okay. All right. Okay, moving along. Couple of things that have to get said. Sometimes you get lucky with the geometry. Y'all will recall I'm a big fan of symmetry. Again, I'll just remind you something along the lines of back of the envelope order of magnitude. I think this is reasonably fair, conservatively fair. In fact, about 20% of the integrals that I saw as an undergraduate, zero by symmetry. Fantastic computational tool, right? That comes from just kind of being heads up and understanding the issues at play there. So here's another very handy computational tool that, again, all it requires is being a little heads up. Sometimes it's not a symmetry thing. Sometimes you get lucky with the geometry. So here's how this problem here we get lucky. So here's the question. We have a pretty ugly parametrized curve right there. And by the way, notice that's not even telling the full story of how ugly this curve is. I gave you the spherical coordinates. That means x, y, and z are going to be sines and cosines of all of that stuff. Right, x, y, this parameterization is monstrously ugly. And if we want to compute a line integral over that curve, right, that's gonna be a pretty ugly, if you're gonna, direct brute force, plug and chug, that's gonna be a horrifying computation, so we would expect here anyway. Okay, and then let's suppose that this is our vector field, and how do we compute this line integral? So the big observation to make is that our vector field right here, notice it is a scalar multiple of the position vector, right? X squared y, that scalar factor that I'm multiplying it by, it's not a constant, right? It varies, right? But it's a scalar, which means that for all x's and for everywhere on this sphere, the vector field is parallel to that position vector. Which means that my field vector is always perpendicular to the sphere. You notice. Here's the second observation we'll make. Notice that complicated though this parameterization is, rho is always equal to 1. That means that every part of this curve, right, it's all on this sphere. I'm confined to the surface of the sphere, which means that my dx vector is always parallel to the sphere. Right? So in fact, then, what we're looking at, let's get rid of all the stuff we don't need. We're looking at this line integral, that line integral right there. Notice the line integral involves the dot product. Right? It's going to be this dot that, which is the dot product of two things that are clearly orthogonal. So that dot product 0, that means the line integral is 0. We drop the pen and we walk away. No fuss, no muss. Right? No nasty calculations. Everybody see how awesome that was? Now, this is a good thing to keep your eyes open for, right? I mean, this happens. As I like to say, the world is full of circles and spheres and round things that have wonderful, convenient geometry about them, right? Ultimately, that's what made the big payoff here, right? The parameterization didn't make any reference to the sphere. The vector field didn't make any reference to the sphere. But the sphere was kind of underlyingly natural to both of them, and making this argument in relation to the sphere is what allowed me to see how easy this problem could actually be. Everybody all right with that? So heads up, right? Be on the lookout for convenient geometry. Sometimes it will make your life really, really, really better. Okay. All right. This is a little bit of notation that I have to mention. Don't worry about this stuff too much. You need to know this, but what I'm about to show you here is going to come off as a little uncomfortable and unnatural and creepy. And don't let that part bother you. Right? It's ultimately not that big of a deal. So anyway, here, let's just dive in. Okay, so we already know what the dx vector is. There's an old news formula, and I can write that out in coordinates. Again, nothing happened there. I'm just rewriting it in coordinates. And then I can kind of distribute and multiply, and then I think it'd be a pretty reasonable thing to take this scalar x prime dt and call that dx. And likewise, this is dy, and likewise, this is dz. So really not much happened here. All I did is basically rewrite the dx displacement vector, displacement differential, in coordinates. That's it. And with that done, notice that allows me to rewrite a vector line integral, because the vector field also has coordinates. So if you just write everything in coordinates, and then check it out, we have an alternative notational option for a vector line integral. And again, this is just nothing's new here, mathematically, really, right? We're just taking what we already had and writing it out in coordinates. So this is what we call a coordinate line integral. It's just an alternative notation for a vector line integral. Is that cool? Everybody on board with that? Here's what's a little awkward. You know, sometimes you'll see, for example, maybe just something like that, just the one term. And what does that mean? What does that represent physically or geometrically? How should I think about that one single term in some sense, and what really kind of should have been three terms? It feels like, anyway. How do you make sense out of that? And this is, one of my dissatisfactions with this notation, and that is it's a little weird. I'm trying to make geometric sense out of that, physical, intuitively satisfying, clearly motivated interpretations of that. It doesn't really work very well. I mean, you could force it. I could make it work, but it just comes off as arbitrary and sort of unnatural, which you really, at least from a immediate physical connection kind of standpoint, yeah, it is kind of unsatisfying. So that's a little weird. What I would encourage you all to do is when you encounter something like this, just think to yourself, okay, well, it's really this, and maybe these other two functions over here, maybe there's just a 0 there and a 0 there. So I could interpret this integral by itself as being, well, it's actually these three terms, two of which are 0, which, as previously noted, is an alternative notation for this, in which p comma 0 comma 0 is the vector field. That's, I think, a pretty reasonable and convenient way to do it. So. Okay, next natural question. Why would we ever do such a thing, right? We have this nice, compact, physically natural notation established. What is dx? It's the displacement along the curve. Very geometrically natural. What is the vector field? It's either force or fluid velocity or something, again, physically natural. But this is a great notation. Everything in here kind of makes sense, right, immediately. Why would I want to rewrite that with this notation that's bigger and clunkier and less physically and geometrically relatable? Who would do such a thing? Where's the payoff? Right? Why am I wasting your time with something like this? So there's a good answer to this. Two good answers. First good answer is that this honestly is a glimpse into some very powerful ideas. So there's this thing called differential forms. You can take a look if you're curious in Chapter 8. And differential forms are a construction that it's kind of abstract and opaque, but ultimately bonkers powerful, super powerful. Differential forms are really important ideas, but they're just, I think, beyond the scope of this course. We're not going to do anything with differential forms in this class, but nevertheless, I want you to know that they exist. Right? I want you to know that there are tools out there that are really, really powerful and really important in doing sophisticated things. And ultimately, this is kind of what they look like. This is what you might call a differential one form. Again, there's really good reasons to do it. We're not going to see any of those good reasons in this course. Nevertheless, those good reasons are there. And because those good reasons are there, this notation is in common use. You're going to see this. I don't know when or where. But almost certainly you're going to see this elsewhere in your probably engineering classes. Again, I know mostly Pratt students. And if you see something like this, I need you to know what to do with it. You can't not know what this is and just be, at a dead end because somebody used a notation that, we don't personally prefer in this course. So I hope that makes sense. So so you're just going to have to be prepared. You're going to see stuff like that. Again, my reaction when I see stuff like this, I just think, okay, well, they meant vector line integral. They're just writing it in a weird way. Okay. Is that cool? Pausing for questions. Okay. All right. Okay, lastly, let's talk about symmetry. So I hope this is no surprise. You look at this theorem, you notice the layout on the page. It's exactly the same layout on the page as, three other theorems that we've previously seen, right? So if you have an integrand that's odd, and if you have if you have a domain that's symmetric, that is, both of these conditions apply over the same line, then your integral is 0. 0 by symmetry. Super powerful, very convenient. Old news. No surprise. I hope no surprise. This is kind of what we would expect to be true. Okay, so I encourage the use of symmetry theorems. Again, warning, be careful. If anything goes wrong and there is no such valid argument, then you haven't given me anything that I can give you points for. And so you really want to think through all those details and make sure that you're right when you apply a symmetry theorem. That said, big payoff when you apply a symmetry theorem. Okay, the asterisk, the thing that is not expected on this is that this only works for scalar line integrals. You'll notice specifically it's got to be a scalar line integral. This does not work for vector line integrals. It just straight up does not work, and you can see why right here. If you're interested in a vector line integral, there's a vector line integral, which of course you can rewrite like this. And keep in mind, the whole thing that makes a symmetry argument work is that you look at sort of opposite pieces, pieces that are paired up by the reflection. Each of these pieces is kind of a reflection of the other, and you argue that the two terms are negatives of each other. But the problem here is, check out this unit tangent vector t. For these two pieces, that unit tangent vector is not, they don't relate. They're not opposites of each other. They're not equal to each other. They're just different. No connection. Swing and a miss. There's no argument to be made about cancellation. There is no odd symmetry theorem. Is that cool? So heads up, be warned. Again, much of a fan as I am of symmetry theorems for any integrals that they work for vector line integrals, like so, you cannot make symmetry arguments. All right, so got to keep that in mind. You got to restrain yourself from trying to do such a thing. Now, here's what you can do, and this is a good idea sometimes. If you are looking at a vector line integral, you can rewrite your vector line integral like this. You know what your vector field is. You can compute your unit tangent vector. You could then look at this as your integrand, see if that is odd, and if so, then you can basically, having reinterpreted your vector line integral as, really, in effect, kind of a scalar line integral, then you can make a symmetry argument about that resulting scalar line integral. So that's fine. That you can do. But again, don't forget, thought of as a scalar line integral, the integrand includes the unit tangent vector. You have to have that computed, dotted with your f, and see your actual scalar integrand. That's the thing that has to have that odd symmetry, not just the vector field itself. Does that make sense? Yeah. Okay. That's 6.1. On 6.2. We're gonna. This is going to be our first step into some very powerful ideas. Green's theorem is a very natural choice, anyway, to be the first example that we're going to see of a bunch of different theorems that all follow a very, very similar pattern. There's a great way to think about these theorems that I want to encourage. That is going to be sort of the focus of my point of view. The focus of how I'm going to present these ideas is how these several theorems that we're going to see all have a lot of things in common. And a lot of books don't. I'd say most books don't do this, which I think is a big missed opportunity. That's just my opinion. But we're going to see in this course Green's theorem, fundamental theorem of line integrals, Gauss's divergence theorem, Stokes' theorem, arguably, depending on how you look at it, a second version of Green's theorem, or some people might prefer to think of it as a second version of Gauss's theorem, whatever. But anyway, 5 theorems right there and arguably, by the way, the fundamental theorem of calculus itself. 6 theorems that are all different on paper. They all can be seen as the results of exactly the same set of ideas. So this point of view about how all these theorems are so closely related to each other, it's actually a very modern idea. So, and there's some history on this. The theorems themselves got thought up in the early to mid 1800s. They're old theorems, a couple hundred years old, right? The full realization of how much these theorems have in common and how you can think of them in a morally the same way, and how they are in fact all special cases of a single unified powerful theorem didn't really get fully fleshed out until I believe it was the 1930s. It's pretty recent. As I like to say it, I know people who knew the mathematicians that came up with this, right? I mean, this is recent stuff, right? So anyway, very, very cool ideas. Obviously, I'm not going to show you the all of the necessary formalities that eluded Gauss, right? No, we're not going to do that in this course. Absolutely not, right? Side note, just for your possible interest, one of the big players, one of the big tools that made all of this modern sort of take on these theorems possible, differential forms. Right? So again, these are some of the big reasons why differential forms are so important, is because they allowed for making connections between a bunch of different theorems and realizing that they're all basically the same theorem. Okay, so that's enough preview. So in order for me to give you the take that I want to give you on how these theorems are all kind of the same, I need to develop some ideas. So the next couple of pages is going to be kind of just sort of a broad discussion. We're not going to actually get to Green's theorem for about 2 more pages. So here we go. I'm going to start with this idea of what do I mean by a quantity on areas. And it's exactly what it sounds like. It's just a quantity. Mass is a nice example. So notice if there's mass distributed all over everywhere, if you give me a 2-dimensional region, we can talk about how much mass is in that region. That's all I mean by a quantity. You give me a region, a quantity gives a value. Right? Simple as that. Okay, so some just to belabor the obvious, some silly examples. Yeah, so mass is a quantity. You give me an area, we can talk about how much mass is in that area. Here's another one. We can talk about area. You give me a region, we can talk about how much area there is on that region. Just an observation. Here's another one. Perimeter. If you give me a region, what happened there? You give me a region, on that region we can talk about what is the perimeter of that region. Does that make sense? Okay. All right. Now here's a tweak of that. Some quantities are special. Some quantities, the way I like to say this, are accumulating quantities. This is just a word that I like to use. You've heard me use that word before. We've actually done stuff with accumulating quantities. This is just a fancy way of saying the whole is the sum of the parts. And this is true for a lot of different kinds of quantities, right? Mass, the whole is the sum of the parts. Of course it is, right? I mean, if you have a lump of clay and it has a certain amount of mass, if you cut that lump of clay into 2 lumps, the sum of the individual masses is the mass of the original whole, because that's how mass works, right? That's just fundamental to, that's what it is, right? Likewise, area, the whole is the sum of the parts. We're belaboring an obvious idea here. Right? That said, this idea of accumulation, as natural as it is for so many different kinds of quantities, it does not apply to all quantities. So, for example, you take this idea of perimeter. Now, perimeter is a quantity. You give me a region, that this gives you a value, but it is not an accumulating quantity, right? So note the sad face here. It's just not, because the perimeter of the whole is like that, and that just straight up is not equal to the perimeter of the one side, which includes that cut through the middle, plus the perimeter of the other side, which also includes that cut through the middle. Green plus orange is not purple in that picture. That stuff in the middle messes it up. Is that cool? So this is a really important distinction. We're going to do powerful stuff with this in just a few minutes. But this idea of an accumulating quantity, where the whole is the sum of the parts, is a really valuable idea as it's going to turn out. Okay, is everybody good? Everybody see what I mean by an accumulating quantity? Okay. So here, for example, is one thing you can do with an accumulating quantity. You can think of it as a kind of a stuff. It's kind of not all accumulating quantities are literally physical stuff, but they behave like physical stuff. I can imagine any accumulating quantity I can think of in my mind. I can think of it as a stuff that's spread out over the area like butter over toast. And so, okay, all right, now this, again, not physical necessarily. I mean, you take like work, for example. You'll recall from the test, right? We had this question about how much work would it take to whatever it was we were moving things over to somewhere, and how much work does it take to move all that stuff. Work isn't a physical stuff, right? But the amount of work that it would take to move all of this stuff, plus the amount of work that it would take to move all of this stuff, in total is the amount of work that it would take to move all the stuff. I mean, yeah, of course it is, right? So this is an accumulating quantity, and I can talk about in a, I think, very reasonable way, okay, we've got a total. How much of that total is in this region right there? And I can just say, oh, well, this amount, right? I've got this quantity. I know for any region, I can talk about what the quantity is for that region. I can think of the quantity for the region as being quantity in the region. There's no problem thinking of it this way. Does that make sense? You can't do this with perimeter. Right? If we were to come back up to here, and if I were to say, okay, we've got a perimeter there, how much of that perimeter is in that little green region right there? That's a nonsensical question, right? So you can't think of perimeter as being stuff distributed over a region. You can think of work as a kind of a stuff. Not physically, but you can pretend that you can kind of in your mind think of it as if it were, because it behaves as if it is. Okay. And so related idea, you can talk about density. So for example, here's how we define mass density, right? It's mass per unit area. Keep in mind, for any given little region, what we're talking about, we can talk about how much mass is in that region. We can divide by what the area of that region is. We can take a limit as this region gets smaller and smaller, and therefore talk about mass per unit area. Old idea, right? Mass per unit area, side note, is the thing that you multiply by area to get mass. Colors. Right? So there's this old idea of mass density, and now what do we really need for this to make sense? What I really need is to be able to talk about how much mass, how much of our quantity that is, there is inside of a given little subregion. That's what you really need. You need to be able to think of the quantity as a stuff. So any accumulating quantity, you can do the same thing. So here's an analogous thing, right? So this idea of population density, and I think we've talked about this in the past. Population density, it's not literally density, right, of the population. It's this different quantity. It's the population count in a given region per area of the region. Yeah? Okay. So population density. Well, I'm going to propose then, if you can do this for any accumulating quantity, you can do this anytime you can think of it as behaving like a stuff. So any accumulating quantity, for example, work, you can talk about the associated density. So now this one's going to be a little bit more sort of like weird and creepy seeming, but we can look at what I'm going to. We can look at what I'm going to call work density. It sounds strange because work isn't a stuff. It's not a physically manifested substance, right? But I can talk about how much work it takes to accomplish a task in a given region. Divide by the area, take the limit. I know that this is going to be a reasonable thing because work is an accumulating quantity. It therefore behaves like stuff, and so this is fine. I can talk about work density, even though it's not a physical density. It's still stuff per unit size in a way that makes sense. And again, this is something that I can multiply by. I can multiply it by areas to get work. I know it's weird. It's weird, but it makes sense. So, in the same way that this notion of mass density allows me to write down a calculation like this, and this gives me a big theorem. I can compute mass as an integral of density, right? Well, you can do this with any accumulating quantity for which you have an associated density. And so weird though it may seem, right? Maybe a little bit unnatural, but we can think of whatever this thing is here, the thing that tells me how to relate work to area. For example, what ended up being the integrand in the example that was on the exam question. Right? I can interpret that as wrong color. I can interpret that as being work density, and I get this theorem that work, the accumulating quantity called work, is an integral of work density. And it turns out this is a really, really nice point of view for a lot of scenarios. The world is chock full of accumulating quantities that we want to be able to do things with, and this is just a universal pattern of things that you can do with accumulating quantities. You can write down these theorems where you say first the whole is the sum of the parts, right? That's the accumulation, and then there's this. I'm going to circle like this. There is this corresponding kind of density argument that allows you to turn this into an actual double integral. Okay. All right. So I'm going to call these accumulation theorems. So this, for example, and that, for example, and any other accumulating quantity where you find the associated density and argue that the whole is the integral of the density as an accumulation theorem because of how important accumulation is in making that all happen. Sometimes I call them density theorems, again, because of the prominence of density in the result. Is that cool? So some of these theorems we've already seen, right? This is old news, right? One of them here we kind of saw, we've seen it in different ways previously, and again it showed up on the exam. Not in this form, right? But we developed an example of this on the exam. And there's plenty of others. Okay, so heads up. We're going to be doing those kinds of things. And now just to be thorough, we argued all of this in a two-dimensional context. You can also do it in a three-dimensional context. You can talk about quantities defined on solid three-dimensional volumes. There are likewise ideas of what is an accumulating quantity. Whole is the sum of the parts. That's all it is. This is what that looks like if you're talking about a three-dimensional solid. And there is likewise the corresponding notion of density that allows you to relate stuff to volume by stuff per unit volume. Okay, so three-dimensional accumulation theorem, likewise a one-dimensional accumulation theorem, same basic idea, except now it's mass per unit, quantity per unit length instead of area or volume. Okay. All right. So that's the background. This is the sort of on which we're going to build a bunch of theorems. We're about to get to the first one. We just need a little bit of background material first. We need to define what we mean by an oriented boundary. And then we'll be able to dive right into Green's theorem. So it's just something that has to get done. It turns out that vector line integrals are going to be the object that we're going to be playing with here. Vector line integrals require an oriented curve. If my curve is a boundary of something, I'm going to need to know what the orientation is. I need to know which direction to go along that boundary curve. So we need a convention. And this convention is, we're going to follow the same convention that's been used for hundreds of years, right? It's a standard. It is arbitrary. Somebody made it up. It's not what I would call mathematically natural. The person who made it up could have made up an opposite choice. That would have been fine. So don't look for magic meaning in this, right? This is an arbitrary choice. However, it is an arbitrary choice that got made hundreds of years ago and which has set the standard that planet Earth has decided to follow. And so even though it's arbitrary, it is not optional. This is the standard, and so we all have to play the same game just for consistency's sake. So the rule is, whatever region that you're interested in talking about the boundary of, as you move along that boundary, the direction that you go is the one such that as you go in that direction, you need the region to be on your left. That's the rule. You always need to walk in whatever direction along that curve puts the region itself, the region whose boundary you're interested in, on the left. So you can imagine in this scenario that we have pictured that our little character right there, right, as that character walks in the blue direction, the yellow region is on his left. Everybody see that? Totally arbitrary. There's a temptation to say, oh, well, doesn't that mean that I'm always moving to the right? No, because the piece of curve could be up above, right? Boundaries kind of go all the way around the thing, and so sometimes it's kind of on the top, sometimes it's kind of on the bottom. Notice that if you're talking about along the top, then that is the direction you go to have the region, again, be on your left. That's what left is as you're walking along that top purple curve. Right? So it's not a matter of always go to the right or always go to the left or always go up or always go down. It's you always have to think about the perspective of movement along the boundary and which side is your region going to be on. Okay, now here's another temptation. Another temptation is students will make the observation that, well, if I go in the direction that puts the region on my left, then notice that wherever I am, I go in the direction that puts the region on my left. Doesn't that mean that that boundary is always counterclockwise, right? You can see from that picture on the left over there, kind of feels like it ought to be always counterclockwise. In many books, it is stated as orientations of boundaries are counterclockwise. That doesn't always work. Just straight up doesn't work. Because here's a perfectly good region, which is tedious to color in. So I'm going to resist the compulsion to try to color that in cleanly. But that region right there, again, it has some cookie cutter holes cut out of it in the middle. And, well, I am sorry to report that on these parts of the inner boundary, notice you would need to go that way to have the region on your left, which would have you going around clockwise, not counterclockwise. So watch out for this one. This is just not true. Saying that the boundary is always oriented counterclockwise is an oversimplification. If you're talking only about the outside part of the boundary, if it is what we call a simply connected, if it's it doesn't have any holes in the middle of it, then yeah, true, counterclockwise. But that asterisk is critical and easy to forget. So I encourage thinking of it this way. Yeah.
So does the region come first or the boundary curve? Like which one defines what?
The region comes first. Oh. So the idea is we have a region. That region defines a boundary curve. And what we're talking about here is how to decide, given a region, looking at the underlying boundary curve, what is the orientation? What is the subsequent orientation on that region? So it comes from the two-dimensional region itself. Does that answer your question? Yeah. Okay. Yeah. Okay. All right. Arbitrary but standard. Okay. All right. So now I've thrown a bunch of ideas at y'all here. Let me just remind you all the ideas I've thrown at you. We have this idea of quantities, this resulting idea of accumulating quantities. We saw that every accumulating quantity can be thought of as being a stuff distributed over the area like a substance, as if it were a substance, even if it's not, but as if it were a substance. And that as such, that substance will, of course, have this associated idea of a density, and we can write down associated integral accumulation theorems. Any accumulating quantity, we can do this. So check this out. It turns out what we started today's class with, circulation. I wrote the word boundary here just to emphasize. Of course, circulation requires that we're talking about a closed curve, which should be a boundary, right? But circulation is an accumulating quantity. It doesn't feel like it should be, but it 100% is. Let me talk through why it feels like it should not be an accumulating quantity. Here is the oriented curve over which I need to do my integral. Actually, you know what? Let me draw this a little differently. This is the boundary of the left side, consisting of those two kind of chunks of curve. And then here's the boundary of the right side, over which I would need to compute circulation of the right half. And now we'll look at the whole. Right? So looking at the whole entire thing, the boundary over which I would need to compute circulation is like that. So I want to compare green and blue versus orange, and again, it feels like there's an inconsistency with this stuff in the middle. Just like with perimeter, the whole point of why perimeter wasn't an accumulating quantity is this stuff in the middle that gets introduced when you break it up. But beautifully, here we're talking about the same edge twice, but going opposite directions. Which means the little green piece left over and the little blue piece left over, they're not zero, but they're exact negatives of each other. Which means that they cancel. So it's like they're not even there. And as required then, the boundary circulation for D1, the boundary circulation for D2, adds up to the boundary circulation of the union. So we've got ourselves an accumulating quantity here. And reminder, when you have an accumulating quantity, it behaves like a substance. You can talk about the associated density. You can write down the resulting theorem. And so, yeah, here's what that looks like when you write that all down. The whole is the sum of the parts. There's an associated density. One thing we're not going to spend time on in this class is how to compute that density, but it's this thing called, that goes by many different names, many different notations. I like to call it Green's operator, and it's just it's the density that you get when you look at circulation as your accumulated quantity. And there's your resulting theorem. And we'll pick up here next time, but notice the punchline is we have circulation computed with a double integral, and that's called Green's theorem. Okay, picking up here next time. See y'all later. Have a good one. Oh, and then let's see here real quick. I didn't have to